Hello, in this lecture we're going to talk about B plus tree. So B plus tree is a tree, has its type of index file. So some disadvantages of having index files. So we talked about index file in the previous lecture. So with index files, it's the performance degrades as the file gets bigger, since a lot of the overflow buckets are created. So it gets messy. It's not a very organized fashion. So some advantages of B plus tree instead of having index sequential files is with the B plus tree, as you keep adding and deleting data, it's gonna automatically reorganize itself. Okay, so it's gonna reorganize the entire file. So you actually don't have to do any separate maintenance performance because it's gonna do that automatically every time you add or delete data. Very minor disadvantage of B plus tree is extra insertion and deletion overheads and space overhead. Okay, so B plus tree is a balanced tree. Okay, so at all times, whenever you're adding something or subtracting something, it has to be always balanced. Okay, so means every path from the root of the tree is the very top node, and then to the leaf of the tree, leaf are all the bottom ones, it's going to be exactly the same length. And each non-leaf nodes, so non-leaf nodes are anything in between the root and the leaf nodes. So anything in between which are non-leaf nodes of the tree has to be between n/2 and n children. So n is a fixed number for a particular tree. So this will be given to you. So usually I'll give you the value of n here is 3 or 4. So depending on that, you will have different number of nodes in each node, number of values in each node. So here is an example of a B plus tree. Up here we have our root nodes, and down here these are the leaf nodes. And these are the non-leaf nodes. We have 2 nodes. Okay, and then, so these are the actual index values. And as you can see, not everything has to be full. Okay, and then these are in between each value or index, you have these pointers. So pointer here is pointing to this particular node. Pointer in between Einstein and Gould is pointing to this node and so on. Okay, and here is a root node. So anything less than Mozart goes here. All of these are going to be less than this value. Anything greater than or equal to, so that greater than equal to will go to this side. Okay, so same thing here. Anything less than Einstein will go here. Anything between Einstein and Gould, but including Einstein, will go here. Anything greater than Gould will go here. Okay, and down here, these are the leaf nodes. So these leaf nodes are not pointing to another node, but is actually pointing to the actual location of the file where it's stored. So here, this particular one is pointing to this one right here where you can find Brent. Over here, this particular pointer is pointing to where Kim is actually stored, and you can access the file this way. So advantages of B plus tree for databases is that it keeps the keys in a sorted fashion because as you can see, anything less than go here, greater than go here, so they're already sorted as is. It does use a hierarchical index to minimize the number of disk reads. Okay, and it keeps the index balance with recursive algorithm because whenever you add something or delete something, it's going to balance it. And so it does minimize waste by making sure that the interior of the nodes are at least half full. So that means that each node has to be at least half full, and that's what we mean by it has to be in between n/2 and n. So it can be full, that's fine, like this is full. It has to be at least half full, so out of 3 index values, you have to have at least 2. If you only have 1 out of 3, that's not at least half, right? So that's not going to be correct. It's not going to be a balanced tree. So the thing about these is that the very bottom ones, the leaf nodes, are the actual data, and anything above, these are actually going to be your index values. Okay, so here we have 2 levels of index values. Your index values are going to be Einstein, Gould, Mozart, and Srinivasan. So you will actually see these index values at the very bottom ones, the leaf nodes, because these are just indexes, and these are the actual values. Okay, a B plus tree is a rooted tree that satisfies the following. So all the paths from the root to leaf are the same length. So that means from the root to the leaf, it doesn't matter which way you go, it's always going to be the same length, right? 1, 2, 1, 2, 1, 2, 1, 2, and so on. Okay? Each node that is not root or a leaf has to have at least half full. So this is where we mean by n over 2 to n children. Okay, so if you have a tree that has 3 index values, yes, you have to have at least 2 out of the 3. If you can fit up to 4 index values, then you have to have at least 2 out of the 4. Okay, and then these are the leaf nodes. It has to be at least half full. Okay, so special cases is if the root is not a leaf, it has to have at least 2 children. Okay, so you can see this one has at least 2 children. Okay, if the root is a leaf, meaning if that's the only value, there's no other nodes but other than just the root, it can have between 0 to n minus 1 values. Okay, so this is what a typical node looks like. We have actual pointers pointing to either another node, or it's going to be pointing to the actual file where it's going to be pointing to where the data is stored. And these are the index values, or we also call them keys. So these are going to be the values. So let's take a look at this example. We have Brent, Calfrey, and Crick. Okay, so anything, so we have this pointer right here. So if you follow the pointer, it's pointing to the location where Brent is located. And anything in between Brent and Calfrey. So if you find the pointer, it's going to be the one where Calfrey is stored, and then this one's going to be pointing to Crick. So this one, what is this going to point to? It's actually going to be pointing to the next leaf node. So if you have another node right here, just like this one, it's going to be pointing to that one. So make sure when you create these B plus trees that the pointers are going to the right place. Okay, so yeah, same thing. Non-leaf nodes, we have the pointer, key, and keys are actual values, and pointer is pointing to either another node or it's going to be pointing to the file location. Okay, so what do we mean by n? So what does that mean? So when we have a value n is equal to 6, it does not mean that we have 6 keys. It actually means that we have 6 pointers. Okay, so we have 1, 2, 3, 4, 5, 6 pointers, and then 1, 2, 3, 4, 5 keys. So it could fit up to 5 keys. Okay, so it's a common mistake that if you don't really know so when you see n is equal to 6, you might think that it fits up to 6 keys, but it's actually going to be 1 less than 6. So 6 minus 1 is 5, so it fits up to 5 keys, and it has 6 pointers. Okay, and then the root has to have at least 2 children. Okay, that's one of the requirements, and it does. So the root has 1, 2, and 3 children. Okay, so whenever you update, you insert, there's several rules you have to follow. Every time you insert something, it still has to be a balance tree. So in this lecture, we'll talk about insertion. In the next lecture, we're going to talk about how to do deletion. Okay. So sometimes you have to split a leaf node when you're trying to add a value to a node and there is no space. It's already full, then you have to split those. Okay, so let's go straight into an actual example. Okay, so here we have a B plus tree with n is equal to 3, so you can also call it degree. So n is equal to 3, or degree is 3, so that means we have 3 pointers, and that means we have 3 minus 1 is 2. We have 2 keys. You can fit up to 2 keys. We want to insert the following: 1, 2, 3, 4, 5, 6, 7. Okay, so we start with an empty node, which we know has up to 2 keys. So we're going to make a box for just exactly 2. So the first 2 are easy, right? 1 and 2. So now we're trying to fit 3 into this node. Is there space for 3 in here? No, it's already full. So we have to split it into 1. So out of the 1, 2, and 3, the middle value always gets promoted up. Okay, so it's going to look something like this. So we're going to split the node in the middle. The middle value out of these three are obviously it's 2, right? So 2 gets promoted up to here. 2 now is an index. And then we're going to follow the same exact rule. Anything less than 2, go to this node. Anything including 2 and up will go here. Okay, so these are the actual data that we see here. This is just an index value. Okay, the next value that we're going to add is 4. Okay, so we go to the root node. Okay, so is 4 less than 2 or is it greater than 2? It is greater, so I'm going to follow this direction using this pointer. Okay, and am I able to add 4 into this node? No, there is no space, right? So what do we do when there is no space? Same thing. We're going to split the node in the middle. So out of the 2, 3, and 4, what do we do? The middle value gets promoted up, which is 3. So we're going to put the index value 3 into this node. Is there a space for 3? Yes. So that's the easiest solution. So you can just put the 3 here in this index root node. And based on that, we're going to rearrange all the values here. So anything less than 2 go here, anything including 2 and up go here, and then between 2 and 3, and then 3 and greater will go here. So now our next value up is 5. Okay, we follow this root node. 5 is greater than 3, so we're going to follow the pointer here, go to this one. Okay, so 5 will go after the 4, right? 3, 4, and 5. Is there space for 5 in here? No, we do not. So we're going to split the node and we're going to promote the middle value. So out of the 3, 4, and 5, what should get promoted up? So between 3, 4, and 5, you're going to promote 4, right? Okay, so is there a space for 4 in here? No. So this will be the most complicated case where you have to split the value or split the node twice in 2 levels. So now we're trying to fit 4 in here. There isn't any space. So between 2, 3, and 4 index values, 3 is the middle one up. So we're going to create another level, 3 here. So that's what's happening here. Okay, so 3 gets promoted up, so we have 3 here, and then 2 is less than 3, 4 is greater than 3, so this is going to be our index value. So we have 2, 3, and 4 index values, and then based on that, we're going to rearrange everything. So anything less than 2 go here, between 2 and 3 go here, and then 3, 4, and 5. Okay, so this is kind of a 2-step process and 2-step splitting. Okay, so make sure you know how to do that. The next value is 6. Okay, we're going to try to put 6 here. Okay, the middle value is between 4, 5, and 6 is 5. Okay, we're going to promote the middle value, which is 5. And there actually happens to be space here. So we're going to put 5 here. And based on the new index, we're going to rearrange it. So 4 will go here, and then 5 and 6 will go to the next one. Yeah, so we were trying to add 6. There was no space in this root node or this leaf node. So out of the 3, middle value, which was 5, got promoted up. There was space in this node, so we just put the 5 here as an index. And based on that, we did 4, including 4 and up, but less than 5 go here, 5 and up go here. Okay, I believe there was another value, 7, that we're trying to add. So let's try that one. So we're trying to add 7 to this one. There is no space, so the middle value that gets promoted up is 6. Okay, is there space for 6 in here? No, because it's already full. So between 4, 5, and 6, middle value is 5. So 5 gets promoted up. Is there a space for 5? Yes, there is one empty space. So we're going to put the index value 5 in there. Okay, and then based on that, these are going to be our index value, 2, 3, 4, 5, 6. And based on that, anything less than 2, between 2 and 3, between 3 and 4, and everything go here. And 6 and up will go here. So ideally, when you're trying to add something and there's space, that's obviously the easiest solution. And if I was trying to add 8 in here, this one doesn't have any room. So the middle value always gets promoted up here. If there's space, great. If there isn't, out of the 3, the middle one will also get promoted up here. If there is no space, it's going to happen again, and you will be creating another level. Okay, so that was one example. So these are the two basic operations. If you're able to add something and there's space, very simple. If not, you want to try to split it. So you're going to split it, and the middle value goes up. We call it promoted up. Okay, so it's always going to be the middle value. Okay, so here I have an example of an insertion. So this is our original B plus tree. Okay, we are trying to add atoms. So where would atoms go? So you go to the root. Atoms is less than Mozart because it starts with A. So I'm going to follow this one. Atoms is less than Einstein. So I'm going to follow this one. And atoms should be right here. Okay, so we have Adams, Brent, Calfrey, and Crick. So out of the four, the middle value gets promoted up, which is Calfrey. Okay, so there is space for Calfrey here, so I'm just going to put that right here. And based on the new values, we're going to rearrange the actual leaf nodes, the actual data, to follow the rule for the roots, the index. Okay, here we are trying to insert Lamport. Okay, the Lamport should be like right here. These are going to be the affected nodes. Okay, so Lamport should be right after Kim. There is no space for Lamport in this root or this node. So between Gold, Cat, Kim, and Lamport, the middle value Kim gets promoted up. Is there a space for Kim in here? No. So out of a Calfrey, Einstein, Gold, and Kim, this one gets promoted up. Is there a space for Gold? Yes. So now we have Gold and Mozart as an index, and then everything gets rearranged based on, the rule that we know. Anything less than Gold, Gold and less than Mozart, and then Mozart and up go here. So these are going to be our index values, and this is the actual data. Okay, so let's go look at another example. So this is how you would do a search. So you want to see where this value is in a B plus tree. Here I'm trying to find 45. Okay, so you always start from the roots. Okay, 45 is not less than 25. 45 is between 25 and 50, so I'm going to follow this one. And is there a space for 45? Oh, actually, we're not trying to answer. We're trying to find it. Follow this one, and we do a search. Is this equal to 45? No. So we go to the next one. Is this equal to 45? No. Next one, it's empty. So that means 45 does not exist in this B plus tree, and it was a failed search. The next value we're trying to find is 15. We go to the root. 15 is less than 25, so I follow this pointer. I go to this node. Okay, we do a search. So we compare. Is 5 equal to 15? No. Is this equal to 15? No. Is this? Yes. This is equal to 15, and we have found it. Okay, so that's how you do a search, starting from the root and just following the rule of, less than, in between these two, and then greater than 75. Okay, so now to this tree, we are trying to insert 28. 28 is between 25 and 50. I'll follow the pointer. I go to this node, and we know that 25 is in between 25 and 30. So we can insert 28 in between this, and we do have space for Q. So this is fine. This is the easiest case of inserting a value. So now we have 25, 28, and 30. Okay, now we are trying to insert 70. Okay, so we go to the root node, and 70 is between 50 and 75. I follow the pointer, okay, and 70 should be going after 65. Unfortunately, there is no space in this node, so we do have to split it, right? So between 50, 55, 60, 65, and 70, the middle value is 60. So 60 gets promoted up here. Is there space for 60? Yes. So there is one space, and 60 goes between 50 and 75. So it's going to be 25, 50, 60, and 75. And based on the new index, we are going to rearrange. So anything between 50 and 60 go here, between 60 and 75 go here, and 75 and up will go here. Okay, so there are just three cases, really. So if you're trying to insert something, there's space. That's the easiest way. If there's no space, then you promote the middle value up to the one level up, and then that gets promoted up here. If there is space, great. If not, then out of those, the middle value gets promoted up, and then you have to create another level. Okay, so those are the three conditions or cases that I just discussed. Okay, now we are trying to add 95. So I'm going to look at the root. 95 is greater than 75. I'm going to follow this pointer and go to this node. 95 should be after 90, but there's no space. So out of the 75, 80, 85, 90, and 95, the middle value is 85. 85 should be getting promoted up here. So out of those, 25, 50, 60, 75, and 85, there is no space in this node. The middle value gets promoted up, which is 60. So you'll have 60 here, and on here you'll have 25 and 50. On this side, I'll have another node which has 75 and 85. So once you're done with the index, you're going to rearrange everything. So same thing, anything below or less than 25 go here, between 25 and 50 go here, between 50 and 60 go here, between 60 and 75 go here, between 75 and 85, and then 85 and up will go here. Okay, so you wanna so whenever you have to promote a value up, you do all of those, and once you have an index, you wanna rearrange the tree to meet the requirements. So every time this tree it's gonna be a balanced tree. You can tell because each of these leaf nodes are at least half full. This is 100% full. This is 75% full. 75%. These two are 50% full, so at least half, right? And then the root node has at least two children, right? Because they have 1 and 2. Okay, so this is now a balanced tree. So I have a couple exercises for you guys to do. Okay, so here we are given all the values that you want to insert into an empty B plus tree. Okay, so if n is equal to 4, that means we have up to 4 pointers, 1, 2, 3, and 4. So the actual keys you can have is 4 minus 1, so you can fit up to 3 values. Okay, so take a few minutes to create this table, and you want to try to show all the steps, especially on the exam, because if you mess up on one of the inserts, the tree will look different. The end result will not be correct. But by showing, each step, so you may have to keep drawing, multiple different trees. Then you will only lose points on the insert that you did wrong, not the whole thing. Okay, so the first three are easy. 2, 4, and 7 will fit right in here because we have 3 slots here. So 2, 4, and 7. Next value is 10. Okay, so 10 does not fit in here. The middle value between 2, 4, 7, and 10. These two could, they could kind of both be the middle. So let's actually try both to see what happens. So out of the 2, 4, 7, and 10, if I go with the middle left, which is 4, what would happen? So let's try promoting 4 up here. Okay, and based on that, anything less than 4 go here, 4 and greater go here. Next value is 17. 17 is greater than 4. I follow this pointer and I go to this node. 17 should be here. There is no space, right? So we have to promote something up. So between 4, 7, 10, and 17, we're trying to go with the middle left, right? So which is 7. Okay, so 7 gets promoted up, and we have 4 and 7. Based on our new index, we want to rearrange everything. So less than 4, between 4 and 7, 7 or greater go here. Next value is 21. 21 is greater than 7. I follow this pointer. 21 should be right here. Between 7, 10, 17, and 21, we go with the middle left, which is 10. So 10 gets promoted up here. There is space for 10. And based on our new index, we rearrange everything. So same thing, less than 4, between 4 and 7, between 7 and 10, and then 10 and greater go here. Last value to be added is 28. Okay, 28 is greater than 10. Follow the pointer. This one is full. So between 10, 17, 21, and 28, middle left is 17. We promoted 17 up here. There is no space here, so between 4, 7, 10, and 17, middle left is 7. So we promote 7 up here, and then we have 4 here, and then 10 and 17. Okay, and based on that, rearrange everything. So remember the conditions of having a balanced B plus tree. Let's check if those are true. Okay, so the root node should have at least 2 children. This one has 1 and 2. That's fine. Remember, I talked about how the leaf nodes, all the leaf nodes down here should be at least half full. So out of the 3, we should be having at least 2, right? But this one has 1, this one has 1. These are all only 33% full, which is not correct. Okay, so this one does not work. So this happened because we went with the middle left value. Okay, so we're going to do the exact same thing, but this time we're going to do the case where we're going to go with the middle right value. Okay, so same thing, we're going to fit 2, 4, and 7 just like we did before. Okay, next value is 10. Okay, so between 2, 4, 7, and 10, middle right is 7. So this time we're going to promote 7 up. The example I did before, we promoted 4. Okay, so we're going to promote 7. Anything less than 7, 7 or greater, go here. Next value is 17. 17 is greater than 7. I follow the pointer. There is space right here for 17, so that's a simple insert. Okay, next value is 21. 21 is greater than 7. We go here. There's no space for 21. So between 7, 10, 17, and 21, middle right is 17. Okay, so 17 gets promoted up here. There is space for 17. So we're going to do 7, 17. And based on that, we're going to rearrange everything. So less than 7, between 7 and 17 or greater go here. Okay, lost value is 28. 28 is greater than 17. I follow the pointer, and there is space for 28. So this is going to be our resulting tree. Let's see if it is a balanced tree. So this root node has 1, 2, and 3 children, right? It has at least 2, so that's good. Each of these leaf nodes are going to be at least half full. This is 67% full. Same thing here. And this is 100% full. So this is a B plus tree, balanced B plus tree. So the point of what example just went over is I wanted to tell you why whenever there are 4 values and you want to pick the middle, you want to always go with the middle right. Okay, so with that in mind, let's try another one here. So we have the same thing, n is equal to 4. Okay, all the leaf nodes should be at least half full. Okay, we want to insert these values. So whenever n is equal to 4, we can actually fit 4 keys, right? One less than this one. Okay, so 1, 3, and 5. Next value is 7. So we try to fit 7 here. It doesn't work. There's no space. Between 1, 3, 5, and 7, middle right is 5. So 5 gets promoted up here. Okay, and based on that, anything less than 5, 5 and greater go here. Next value is 9. 9 is greater than 5. I follow this one. There is space for 9, so I'm going to insert that. Okay, 9. Next one is 2. I go to the root node. 2 is actually less than 5, so I'm going to follow this pointer, go to this one. And 2 should be in between 1 and 3, and there's actually space for 1. So now I'll have 1, 2, and 3. Okay, next we're going to insert 4. 4 is less than 5, so I'm going to go here. Is there space for 4 in here? No. So between 1, 2, 3, and 4, middle right is 3. So 3 gets promoted up here. There is space because there are 2 empty slots. So I'm going to put 3 and 5 here. And based on that, anything less than 3, between 3 and 5, 5 or greater go here. Okay, next one is 6. 6 is greater than 5. I'm going to follow the pointer. I'm trying to insert 6 here. So between 5, 6, 7, and 9, middle right is 7. 7 gets promoted up here. And based on the new index, we rearrange everything. Next one is 8. Okay, so 8 is greater than 7. I follow the pointer. And there is space for 8, right? There's one space. So this will now be 7, 8, and 9. Okay, that was an easy insert. Last one is 10. Okay, so I can already tell it's going to be difficult because we can see that this node is already full, this is already full. So we're going to have to do a two-step process of splitting and promoting. So 10 is greater than 7. I'm going to follow this root node, this pointer, and 10 should actually be right here. So it has to get promoted. So between 7, 8, 9, and 10, middle right is 9. 9 gets promoted up here. There's no space for that. So between 3, 5, 7, and 9, middle right is 7. So 7 gets promoted up here, we'll have 3 and 5 here, and then we'll have the 9 here. Based on our new index, we rearrange everything. So anything less than 3 go here, between 3 and 5, between 5 and 7, between 7 and 9, and the 9 or greater go here. So this will be like the only case where it gets really confusing because you have to do the promotion twice.